Good evening, ladies and gentlemen. Welcome to our first episode of Q&A in data analytics. And tonight, because it's, as you can see, middle of the night for me, I'll try to answer your first batch of questions. Questions were sent by 3 people altogether, but I got also from one question from Mr. Mularczyk regarding your grading, and we'll get to that later. Either way, questions are mostly related to the first topic, that is one parameter models, but some of them are rather general, so we'll try to discuss them as they come along. I will keep the authors' names confidential. If someone really wants them to be publicized, let me know and I will mention them in the next video. So let's go to our first question. And what is prior probability? There was also some supporting questions. Is it only a term about prior data set that we have? Is it only data based on which we are creating model and trying to predict next results? I want to mention at first that I am editing a bit the context of the exact verbiage of this questions in order to make them more useful for the video. So generally, prior probability is really what do we know about the problem before seeing the data. This might be our prior experience. This might be expert knowledge that we get from people that we are working with or from what we were doing before, and prior probability encodes our information that we have our process without looking at data. If we have good information, our prior might be very strongly indicative about the behavior. For example, when we were using the model from cancer rates, in the cancer rates model, the death rates were we had a very strong prior that gave us the shrinkage to the mean of that prior. That is, if there were too little informations, then we're getting more. If there were, for example, no deaths, then we got extra. Then we got extra movement of our estimated death rate upwards, and if we're much more, then they will move downwards to our prior. We will return to that plot in a bit. If we don't have good information, then the role of prior is mostly regularization, because there was some years ago there was an idea of using completely non-informative priors, which is now being people are moving away from that, and there is very rarely a situation that you don't know anything. And if you know anything, even about the ranges or the scales of what you are working on, that's a lot of good information that will allow your algorithm to avoid that areas in the parameter space. And really, we should, on one hand, from classical approach, our prior should not be related to our data, but, and this is the entire concept of prior predictive checks, that we want to make priors that make sense. And if we don't have good information or a priori knowledge about what can be possible results when we are simulating from our prior, we could at least check if our data makes sense in this model. We are not trying to use prior by itself to estimate the data, but we just see if the data is possible. If the data is not possible to our model, then there are some questions. Either our model is wrong, which is more probable, or our data was very unusual. So if we are very confident about our model because we've used expert knowledge to create the priors, and we get something that is completely inconsistent with the data, we need to recheck our data. Where we get them from, what's wrong with them. So that is our first indicator. So this is a situation that we can look at data and use them. Other aspects are, for example, looking from the data, we could get some information about scales. that we have certain scales of the data that might be used, that we can use to get some regularization, that we have our data is not spread too much. But like, don't look too much into data when designing priors. Certain information can be inferred, but on the level of weak priors. So we are not introducing much information. We were doing weak priors, for example, when estimating the parameters of half normal distribution that we assigned for lambda in Poisson's distribution. Okay. Next question. Does Bayesian statistics always have two possibilities, 0 or 1, success, failure, man or woman? Anything is possible! Everything is possible. Bayesian methods can be used for multiple cases. We can use them for images, we can use them for counting data, we can use them for, like, for Poisson distribution, we can use them with continuous data, like with normal distributions, or other, like, we have parameters that are varying, that their values are real numbers. Positive, negative, never mind, but like real numbers. We can have time series data, so the data that is a series of samples that are ordered by precedence, like for example data from dynamical systems or observation of historical data. We can use Bayesian models for natural language processing, and much more multiple options that what we can do. We can do for spatial data, like localization of even the space, estimating the composition of geological areas. There's like multiple possibilities of using Bayesian models are limitless, so we don't have to worry about that. So hopefully that solves. Next question: is prior predictive distribution done only on Bayesian models? In short, yes. This is because we need to have a prior distribution. If we don't have prior distribution, we can create a prior models. Existence of prior distribution is something that makes Bayesian models significantly different from classical statistical models, because classical statistical models do not approve using any knowledge that you have outside of the data for your inference. Because of that, they propose different constructions that might be work, like for example bootstrapping, so sampling from your data multiple times from your data to generate some kind of, let's say, fake data that is similar to your original data. Classical statistical methods work very well if you have a large number of data. So like when your n of number of data tends to infinity, classical methods work very well. In case if it's significantly lower than infinity, then problem starts, and here Bayesian methods are superior. But that's why they are using, because they are using prior information, which can compensate you for the lack of your data, or can provide you valid info about if your data is reliable or not. Okay, next question: is Poisson some kind of subgroup of Bayesian models? But Poisson models can be used both in classical statistics and in Bayesian statistics, but you should know that they are they are one of many models generally for counting data and or integer value data that can happen in certain situations. Poisson distribution has this effect that it has variance and mean are equal to each other, and this is can be represented. Some of not real cases that happen are really well fit for that such situation happens, because Poisson distribution was derived from observation of binomial distribution in multiple cases. However, you can look for some generalization of Poisson distribution that will allow you to avoid that situation. For example, there is a larger variance or than mean, or a smaller variance than mean, and then for example used negative binomial distributions, which allow you to generate your probabilities of certain integers but without that constraint, and Negative binomial distribution is a topic of one of the exercises that you will be doing. You actually should be doing at the moment. So Poisson models are used also in classical statistics. However, they are usually approximated with normal distributions because that makes computation much easier analytically. And for larger values of theta, there is really very little difference between Poisson and normal, at least on the numerical scale. You just need to remember to keep to the integers. Okay, and from probably the last question regarding Poisson distribution is what's going on with this equation, that is lambda plus 3 square root of lambda approximately equals 365. We've used this equation in order to estimate the upper bound for the probability distribution of parameter lambda. Why is that? This comes from generally from normal approximation, and the classical result regarding normal distribution that 67% of probability mass is in the interval me minus sigma to me plus sigma, 95 is minus 2 sigma and plus 2 sigma, and 99% is minus 3 sigma plus 3 sigma. And sigma is of course standard deviation, so it's the square root of the variance. So having 99% of probability mass in this interval is interesting for us because this is something that we want to have. And Poisson distribution is well approximated by normal, so having that, because our Poisson distribution has this case of variance equal to the mean and standard deviation is the square root of variance, then if we want to be sure that on 99% situations we will have less than our lambda coefficients will result for us with less than 365 in this case accidents per year, then we need to have that this upper bound is equal to 365 days. So we need to compute lambda in a way that will fit this situation, and that's what we actually did. And regarding further questions of prior tuning, why we are using logarithms in the computation? This is actually a question regarding the code of calling the function for tuning the prior. In standard model we were using the algebraic solver in order to find the solution of the equation, and really the question is why we are using logarithms in such computation. And using logarithms comes from the fact that it helps us avoiding rounding errors and helps us avoiding flatness. Look, for example, here. Here we have the plot of typical normal distribution on the range of from minus 10 to minus 8. So relatively small. It could be also positive away because it's square, but in this case we have very small numbers. As you can see, we have here, by changing this number, we have spread from almost 0 to 1.604 times 10 to minus 28. These are very small numbers which are differing very badly with each other. Here on this scale of two integers of like changing to between 10 and 8, there's not much difference. We have almost flat function with large spike, which is really not something that you can observe, but this is in a very minuscule scale. However, if you consider a logarithm of this value, then you have a spread from normal numbers, numbers in the same order of magnitude, from minus 43 to minus 27. So you have easily, you can distinguish elements on this scale, and this is also very useful for numerical computation, because when doing numerical computation, especially gradient-based numerical computation, it's very risky to be found in such flat regions, because then the derivative will also be very flat and our movement of our algorithm will be very slow, because the value of the derivative is very, very slow. And if you move from that to the logarithm, then this rate is completely different. This generally behaves like a square function. And because of that, it's much, much easier to do gradients, to do anything. So that's why we are using the logarithms in such computations in order to avoid such problems. And for example, in case of passing arguments to estimating the half normal distribution parameters, then we just provided it so we could have a good start without any rounding errors or having large numbers that we would not like. And our final question about pair of tuning, why we were setting only the upper bound when tuning the probability distribution. Because as we have seen here, it should be the range from plus to minus, from mean to plus 3 sigma and minus 3 sigma. Why we haven't using the lower bound? Well, we haven't used lower bound from that because we weren't assigning normal prior. We were assigning a half normal distribution. Half normal distribution is generally a distribution of what would happen if you take an absolute value of random number samples. So for every negative value would just be transposed as positive. This distribution is naturally constrained from 0, so our assignment of lambda and getting the half normal prior that will get us lambdas for 99% will give us lambdas from 0 to 312, which was the solution of the equation we've seen before. Then this situation was in this case we don't need to look from this side because all our probability from here is just located this 99%. So we have a lower bound from here, so natural lower bound from 0, so we don't have to care about it. Lambda must be just greater than 0. It shouldn't be, it cannot be negative. Okay, and that was that for the prior tuning aspect. Let's go to our next question, and the next question is generally what's the difference between prior and posterior predictions, because we have seen these predictions and why the prior posterior are better than prior. That was the question explicitly stated. So let's look at this prior predictive and posterior predictive distribution. First of all, they have completely different goals. Prior predictive distribution is the just in this case used to see that if our data is realistic. Is it realistically fitting for what we wanted to fit? So if our data is consistent with our prior, as our prior generating something that is related to, or is at least it makes our data possible. On the other hand, posterior predictive distribution is created after seeing the data. Here we're just checking, okay, it makes sense. Here we are trying to infer if our model is okay and what is going on. And we are doing this retrodictive analysis. So like really we are checking are the outputs that we observed, or the values that we observed are the same as previously. What you should notice that the black lines are the same on the both sides. Black side is a really observed value. Histograms show you what was simulated from that. As you can see, values actually, because those distributions are continuous or semi-continuous, really, because we have multiple values, the vertical values here on the x are not that important. What is really important is how the area under the probability curve is distributed. As you can see here, it is on much thinner area. Here we had the up to 365, sample up to 365. Here we have the spread from let's say 16 to 50, so somewhere up to 50, less than 50. This is our complete distribution. So we have much tighter intervals of what we can expect. Remember that we have a little amount of data and we had a very simple model. So our model is the problem that we see here, that while from this model we just only seen that actual data, it does not contradict the model, the priors, but when this model we've used and we fit it with real data, we see that our model does not capture the systematic effect. The systematic effect of changing numbers of accidents in in an opposite way than an increasing number of flights, which actually is the next question, where we can see that more flights, more accidents effect. We cannot see it here, because here is or on the predictions for the next slide, because here we don't have explicitly seen the numbers of flights, but we can look on the data. And I haven't mentioned during the lecture because I've assumed that you've noticed it, but really I've spent on this data set much more time. So generally, number of flights were growing over time. So every year from 76 to 86, actually, it is not here, but you can find the data in the notebook, we got more and more flights, with an exception of 1982. And number of fatal accidents were either on the same level or even dropping sometimes. So seeing that, there is some kind of systematic effect with time, that with time number of accidents was dropping, at least in the proportion to the milestone here, and our model wasn't capturing that. So we'll do that as an exercise in the regression modeling. I'll just show it in the regression modeling modeling lecture. What's going on? So that was observed in the data, and it wasn't really visible on those plots. Okay, so our next question leaves us from the flight data, and we move to the cancer data. So our model with the more predictive distribution. And really, the question was how to interpret the predicted versus actual plots, because I was made aware that it wasn't that clear what was going on here. So let's look at such plot. Here we have on the x-axis we have the observed death rate, and at the vertical axis we have predicted death rate. And really, what's going on here? First of all, in this plot, if the observed death rate is a very noisy estimate of actual cancer effect on the populace. So that we haven't observed something doesn't mean that it isn't there. Especially in small counties, that's not an issue. In this figure, we have the gray vertical lines, which are actually black ones, but with appropriate alpha coefficient in order to avoid overlapping them and covering everything. Are the error bars. For each of those dots, we have a vertical error bar that says how much uncertainty we have here. And if I remember correctly, it was a 95% interval for each of those samples here. And our model was observing the data, which is from here, so how many people died in that area relative to population size, because this death rate is the number of deaths to the population size, was estimating our results. And from our prior was very informative one. We gave it a strong prior, giving a preference where are the appropriate values. So it's not 0 and it's not very high. So our prior was shrinking our predictions from the observed rates closer to the median. And here we have the error bars for all those samples, and as you can see, especially here, all those error bars cover the line. So our model allows our prediction to be equal to the validated, to the observed death rate, but it assigns more probability that it's lower, it's closer to the median, because our data wasn't indicative enough in order to combat that prior experience. And really, that prior was very informative, but not necessarily was very good. And second, this model was very simple. because this model assumed that really for every county in the US there's a different death rate, and those death rates are not related to each other. And really this model asks for a hierarchical model that would, for a multi-level hierarchical model that would join certain areas with each other. For example, assign even to a state, and from that state estimate certain rates, because the estimates here have sense not only because the cancer is more lethal by itself, but for example, healthcare is worse in certain areas. So that's why proper assignment of those priors might be more difficult. Either way, gray lines, which here are so much overlapping that they are almost black, are the uncertainty. The dashed line here is the situation where observed rate would be equal to the predicted death rate. If the points are here, the observation is exactly consistent with the median of our estimate. However, in all cases, when the death rates were observed very small, we are moving upwards to the median, and with the observed higher, we are moving downwards to the median. And this is caused by the shape of our prior distribution. You can check again in lecture, where generally most of the probability is of the prior is in the small values, and all above that is all values above that are strongly damped to zero. So there is you need to show a lot of evidence that the death from those the considered cancer is here. So, and our next question is a more river question. It's like it's a giant topic which I won't be covering here now, but I will give you some highlights because I want to make a full video sometime in the future about that. But now just a few highlights about that. This analysis is based on the great paper of Michael Bethancourt explaining how Hamiltonian Monte Carlo and Monte Carlo Markov chain methods work, and I strongly recommend you to read it. It's in the archive. You can find it in the episode notes. So, an episode description. So really, what's going on here? The main problem that we have when doing sampling from our distribution, so we want to generate samples from certain probability distribution. This probability distribution is very complicated. Usually, we have multiple parameters with complicated relationships between each other. What is even more difficult is that we don't want to generate those samples from anywhere in this distribution. We want to be located in something called a typical set. Typical set is the area where there is a most of mass of probability distribution in the which we want to integrate, because really we want to compute some kind of expectation using Monte Carlo estimator. So we want to, for example, get a lot of samples and compute the mean of those samples. And the problem is that the finding the typical set is difficult, and we want to get samples from this typical set. The problem is that the finding the typical set is not obvious. It cannot be really done analytically. So what can we do? We can create a sequence of values that approaches typical set and stays in it. And for that, we are moving to Markov chains, because Markov chains are stochastic processes that generally is a sequence of points in the parameter, in our case in parameter space, that next point is a transition from a previous point. So we made some kind of step for our previous point. And if Markov chains are well designed, they can preserve distributions. What does it mean? This means that using samples from Markov chain, so a process that reaches typical set, when we try to get our values from those Markov chains, so elements of this sequence, and we ignore the sequencing facts, so we ignore that one sample comes from another, we just look them as samples, those samples will have the distribution of our interest, if of course the chain was generated in the proper way. But properly generated Markov chain, in case of Monte Carlo methods, in the context of Monte Carlo methods, will get us samples from the distribution, and this is what we want to do. And how does it work? Well, we start. The main issue of Markov chain evolution is that starting from one point, it has a probability of moving generally anyway, and step after step, it moves somewhere, is wandering around the space. The distribution preserving Markov chain converges toward typical set. So if you have our typical set, its shapes that you can move stop being circles, moving any way you want. It will start moving, assigning more and more towards the typical set, and less backwards. So properly designed distribution preserving Markov chain will find out the typical set for us. And that is something that we've observed before during our lectures when we were running STAN programs, the warm-up phase. The time for Markov chain to reach the typical set. Typical set, as you can see, can have a complicated geometry. So you are approaching the typical set. And on this figure here, we have the error between actual expectation and the expectation estimated from the samples that we get. So initially, the error is large, but it's justified because while we were sampling from our distribution in some kind of way, we haven't reached the typical set yet. When we reach the typical set, we start wandering around it, and our errors is rapidly growing now. But if we go further, we are doing some refinements. So we've previously explored the typical set, and then we are refining its context. We are looking exactly what's going on here, and then we improve our errors for the Markov chain estimate, for the expectation estimate. And this is what I want to say now. Later we will discuss more what kind of methods are implemented in STAN, how does it really work, and why this typical set issue is important. So we move to our next question, and this is the last question of regarding topic, because topic of lectures I've received it from one other person. Why there are no units when I'm describing what's going on? Well, as you've seen some actuators, units will started happening, but really they are units when they are needed. Probability by itself doesn't have units. It's a number between 0 and 1. You can express that for convenience as a percentage. So for example, you had 60% chance to do something, but probability by itself doesn't have units because those units make no sense. And even more, I'm not often not showing you the values of the, for example, probability distribution function. We're just looking on the arguments, on the range of the arguments. Why? Because what's more important is that how the area is distributed. Actual values are not that important, because depending on the range, you still have to integrate it to 1. If the range is very wide, where the distribution is located, then those values will be very small and does not mean that much. What it means is how this entire 1 is distributed in the area. In case of count data also they are integers. They are not dimensionals. So again, putting units in there. However, in later lectures, you've seen that we had units for multiple cases, like for example, medicine dose or something like that. And now let's move to the more organizational aspect that you were also interested in. And the question was, what questions will be on the exam? So this question is, let's say, it's not that tricky as you could actually think, because all questions will be available before the exam. you will receive the list. The list will be placed on GitHub. There will be full list of things that I will be asking you. Every person on the list that will be attempting the exam will be assigned 3 randomly selected questions. I will just put a random number generator and assign one of those, let's say 30, 50 questions. Not sure how many will be there, and 3 of those questions will go to everyone, along with their sequence, which will also be random. During the exam, I'm asking you a first question. If you answer that question, great, you passed. If you fail the first question and you fail the second question, you failed. If you answered the second question and you answered the third question, because you are only asked them if you failed the first one, you have passed. And if you have failed the third question, you have failed the entire exam. So you have 2 possibilities of positive outcome and 2 possibilities of negative outcome. So really, the focus is that if you fail, you have to rehabilitate yourself by answering 1 question more. So you have to cancel this negative balance of wrong answer, and then you need to you need to be given questions like starting from 0. So that's the formula of the exam, and everyone will have 3 approaches. If you can do it like the first one we will do, of course, in June. However, the rest of them will be generally will be flexible regarding the topic. It's more when you will want to get the exam done. Of course, not regarding the exact hours, but regarding the day or the time of the during the summer. It's up to you. We will be doing the exam on MS Teams, and I'm not sure yet about the recording, how it will be going. Will I be recording or not? I was informed that with MS Teams, those recordings are being made only on the server, so it might be a technical problem with that. Also, I need to check with the dean how is it formally with recording of the exams, but like I wanted to have to do for everyone to have the copy of such situation, so there will be no debatable things and no problems in the further. And one question that wasn't asked directly to me, but it was passed to me: how will be grading the laboratories? And you will have received 2 more exercises to do. The first one will be a Poisson model that is similar to the airline models. Actually, it's an airline model, but on slightly different aspect of the same data. And the second one will be a regression model. We will be doing linear regressions next week, so you will see the series of videos on linear models. And after that, we'll have projects. Projects will be significantly reduced in scope from what I wanted before, but they will be individual. And you will be doing your own data sets, so you can start looking for the data sets that you want, because you will be there will be an extra video about how the projects will be done, but generally you will need to find your own data set, and you will be creating model from that data set, and you will do those Bayesian things with that in order to evaluate its probability distribution, predictive, prior predictive distribution, posterior predictive distribution, certain extra Bayesian checks we haven't talked about before. So that will be it. And ladies and gentlemen, that's all for tonight. And remember,
now we know.
And knowing is half the battle.